Welcome to the class on quantum mechanical tunneling. Let's take the case of a particle of a definite energy approaching a barrier or a region having a higher energy. So according to the concept of classical mechanics, the particle cannot enter the other side. It will bounce off. But according to the principles of quantum mechanics, there is a definite chance for the particle to penetrate the barrier and reach the other side. This phenomenon in which particles of lower energy can cross a boundary with a higher energy is called as quantum mechanical tunneling. We discuss the case as shown here. A beam of particles of kinetic energy E travels from the left, that is region 1 shown by that yellow arrow. Now that beam is incident on a potential barrier of width L and height V, that is region 2. On either side of the barrier, potential V is equal to 0. And to the right of the barrier, the region is denoted as 3. And now we will apply Schrodinger equation in each region separately. In region 1, since capital V is equal to 0, the Schrodinger equation takes the form dou square psi 1 by dou x square plus 2m by h bar squared E psi 1 is equal to 0. It is not E minus V, it is E psi 1 is equal to 0. And the solution is of the form psi 1 is equal to a e raised to I k1x plus b e raised to minus I k1x. In this, the first term a e raised to I k1x represents a wave travelling towards the right in region 1, that is, which is incident on the barrier from the left, which is shown in red arrow. This wave strikes the barrier at x equal to 0 and is partly reflected and partly transmitted. And the reflected wave is denoted by the term b e raised to minus I k1x. Now we will go to region 2, and there the term v is not equal to 0. Hence the Schrodinger equation takes the form dou square psi 2 by dou x square plus 2m by h bar square E minus V into psi 2 is equal to 0. And the solution for that equation is psi 2 is equal to c e raised to minus k2 into x plus d e raised to k2 into x. So here please note that the term I is not present here, that means psi is not a complex quantity. Here the first term c e raised to minus k2 into x represents the wave travelling towards the right within the barrier. And d e raised to k2 into x represents the wave getting reflected at x equal to L and travelling towards the left. And since mod psi 2 square is not 0, there is a chance of finding the particle within the barrier, and such a particle emerges into region 3. Now in region 3, again V is equal to 0, hence the equation takes the form as shown here, and psi 3 is equal to f e raised to I k1x plus g e raised to minus I k1x. Here also the first term f e raised to I k1x represents the wave travelling towards the right from x equal to L. But there is nothing to reflect the wave towards the left. So, in the term g e raised to minus I k1x, g is equal to 0. Hence, psi 3 is equal to f e raised to I k1x alone. So, depending on the region, Schrodinger equation takes different forms as shown here. Now the term transmission probability, it is defined as the fraction of particles that succeed in tunneling. That is, T is equal to number of particles per unit area per second that emerges from the barrier divided by number of particles per unit area per second that arrives at the barrier. T is equal to e raised to minus 2k2 into L. That's all. Thank you.